So welcome to the last lecture on Riemannian symmetric space. Actually, this lecture is dedicated to Thangabelu sir. Actually, words are really insufficient to describe his role and contribution towards harmonic analysis and development of harmonic analysis within India. So I think all of us are grateful to him for that. Okay, and this lecture is also happening because of him. And on behalf of everybody present here, I wish him very happy and prosperous life and good health in future. And with his blessing, let me begin the talk today. Okay, thank you, sir. Okay, so
thank you very much. Thank you very much for these lectures.
Okay, sir. Thank you, sir. So it's lecture 35 and so actually in the last lecture I have calculated this center of some familiar groups. I have added 2-3 groups there, and I will after some time I will also add more groups. Okay, so you can read those things. So today
Muna, just excuse me, just a small remark. You may sometime think about typing these notes also.
Okay, yeah.
And
yeah, I will
put it on your homepage. You can do.
Yeah, I will try to do that. Okay, so so last lecture we have calculated some center of group. I have added 2-3 examples more, and later on we will add some more examples. So so I will basically calculate 2-3 killing forms. So first actually I will start with a proposition, simple proposition probably which you will know. So so let T is equal to really x belongs to MNC. Okay, so that this x has distinct eigenvalues. So then this D is dense in MNC. Okay, and proof is very so any complex matrix is triangulable. Okay, so let A belongs to MNC. So then there exists G belongs to GLMC, so that A is equal to really G lambda 1, something like upper triangle lambda 2. This is lambda n, and this is 0 and G inverse. So see, the thing is this lambda 1, lambda 2, lambda n may be same or different, but these lambda 1, lambda 2, and lambda n are really eigenvalues of A. Now what I do, I will perturb these diagonal elements in such a way that small by small change, I can perturb these diagonal elements in such a way that that will sufficiently that matrix will lie sufficiently close to A, and these diagonal elements are distinct. So, and that will prove that this D is dense in MNC. Let me write that precisely. So let U be any neighborhood of A in MNC. Clearly, there exists epsilon 1, epsilon 2, epsilon n, epsilon 0, so that this lambda I f plus epsilon I not equal to lambda j plus epsilon j for I not equal to j. Okay, and one thing.
Muna, just go back once more. So there exists neighborhood U.
Let U be any neighborhood of A. Clearly, there exists epsilon 1, epsilon 2, epsilon n greater than 0. So that lambda I f plus epsilon I plus lambda j plus epsilon j for I not equal to j. Okay, and this, if I define this A tilde, this G lambda 1 plus epsilon 1, lambda 2 plus epsilon 2, and lambda n plus epsilon n. This G inverse, and there I will keep the same matrix here, same elements here. So this is this belongs to you. This is possible. If you do small changes, then this is possible. So clearly this A tilde has distinct eigenvalues. And A tilde, this clearly A tilde, thus D is dense in MNC. So this is a clear thing. Now, if X has distinct eigenvalue, then that is diagonalizable, right? So as a corollary, set of all diagonalizable matrix, complex matrices are dense in MNC. So this is the thing. Now there is a warning. So the first thing, the above corollary is not true for real matrices. And second thing, that will imply that if this corollary is not true, then consequently the above proposition is not also not true for real matrix. This is because okay, so that means actually in this proof, actually we will use this thing that C is algebraically closed. Okay, so this is the thing I want to say now. Some sound is coming. Okay, so now
this can be done for any algebraically closed field, right?
Actually, you have to put a topology there, and many things are there.
Topology, there is a field, so you can put topology, right?
Probably, I think I'm not sure. I do not know about other fields, like KP or something. So
you can put a topology by defining a valuation. So you can always do that.
Might be the case. I do not. I'm not sure. Okay, so this is really, I will computation of killing form. So killing form of MNC, and MNC is nothing but GLNC, right? So first thing, so we will show that. So let B be the killing form of MNC. So we will show that B of xy, I have written this expression. This is 2n into trace of xy minus 2 times trace of x into trace of y with x comma y not to elements. Okay. Now, since this thing, you look at xy going to really 2n trace xy minus 2 trace x into trace y is a bilinear form on MNC. So in view of polarization identity, suffices to show this thing B of xx is equal to really 2n trace of x square minus 2 into trace x belongs to MNC. So what I am saying that if you check there that xy going to 2n trace xy minus 2 times trace of x into trace of y, this is a bilinear form on MNC. Okay, you check that, and the killing form is also a bilinear form, and there is a polarization identity. It says that polarization identity you will get that if two bilinear forms are agree on diagonal, then they are basically same. So if I can show that B of x comma x is equal to 2n trace of x square minus 2 times trace of x square for x belongs to MNC, then I am done. So our claim is really something like this. Claim B of x is equal to 2n trace of x square minus 2 times trace of x square. Okay. This is x belongs to MNC. This is our claim. Okay. Now this thing, if you look at this thing, Eij, okay, this is really 1 less than equal to I comma j, this less than equal to n. This really forms a basis of MNC. And what is Eij? This is ijth entry is 1 and rest are 0. You know that. And you know also this calculation Eij KL. This is delta jk EIL. So let delta is equal to really, I define this set. This H belongs to MNC. So that H is diagonal. So this is really a subspace of MNC. If you now the thing is, if you let H belongs to delta, then you can write this thing. H, you can write this thing really summation of I is equal to 1 to n. So EIH EII. So basically H is equal to really this thing E1H E2H. This is really ENH.
What is the meaning of EIH?
EIH is equal. See, the thing is H is equal to some diagonal element H1, H2, Hn, right?
Okay, so ith entry. Okay.
I am calling this H1 as U1H, H2 is equal to E2H. Okay, that's good. Now, so what is trace of H? This is really summation of i's. Okay, let us write first H square. So H square is equal to really, so diagonal of this thing E1 H square, E2 H square, and this is really E and H square, right? Now what is trace of H square? This is equal to I is equal to 1 to n EIH square. Now what is trace of H? This is really I is equal to 1 to n EIH. Now what is trace of H whole square? So I can write this, that is trace of H into trace of H. In one trace of H, I will write something like this, y is equal to 1 to n EIH. And another thing I will write like this, j is equal to 1 to n EJ. So that is really summation I j EIH into EJ. So remember this thing, trace of H square is equal to really EI summation of I is equal to 1 to n EIH square. Call this as A, and I am calling this as B. Trace of H square is equal to B. Okay. Now, now R of H EIJ. This is really H EIJ. Now what is H is here? This is really M is equal to 1 to n EMH into EMM, right? And this is really EIJ. So I can pull out the sum outside. So EMH, this is really EMM EIJ. It's a very simple computation. So M is equal to 1 to n. This is EMH. So this is EMM EIJ minus EIJ into EMM. Okay, so this is really M is equal to 1 to n. So EMH EMM EIJ minus M is equal to 1 to n EMH into EIJ into EMM. Look at this expression carefully. This is non-zero if this is non-zero if and only this M is equal to I. So everywhere there will be I. Okay. So in that case, this will be really EIJ. So this will be EIJ. Okay. So this let us not write it. Now, similarly, this is non-zero if J is equal to M is equal to J. So this will be J everywhere. So let us calculate the first expression then. So this will be EIH and EIJ. That means this is really second thing will be EJH and EJJ. Okay, so this is the thing. Now, so this will be EIH minus EJH EIJ. Hence, I get the RH of EIJ is equal to really EIH. Yes.
On the second last line will be EIJ. EJH minus EIJ.
Thanks. Sorry. Okay, thanks. So this is really EIJ. Now that means RH is a diagonal matrix. Actually, if you look at the matrix representation of RH with respect to this basis EIJ, this is a diagonal matrix. And what are the diagonal entries? These are really EIH minus EJH. Okay, that is correct. Now I look at this thing. So RH square EIJ this is equal to EIH minus EJH whole square. This into EIJ. Okay. So now this RH square. That means.
No, how are you saying RH is a diagonal matrix?
Because this EIJ is a basis, right?
Yes.
So RH is a basis. With respect to this basis, see the thing is diagonal means TBI is equal to lambda IBI, right?
Yes.
So this is my BI is EIJ.
So there are n square many of them, right?
This I am having this 1 less than I comma j less than equal to.
Yeah, so there will be n square. So basis of the n square matrix, right?
No, the matrix will be n square by n square matrix, and the diagonal entry will be n square.
What is the problem, Tapendu?
No, that is all right, no. What you written is correct.
Manoj, is it clear?
A little bit confused. So RH will be a matrix of what dimension?
N square cross n square.
N square cross n square. Okay, fine.
So EIJ are the basis. EIJ are the basis of MNC, right?
Yeah, correct.
Okay, so let us write this thing. So B H comma H, this is really a trace of RH square, right? And this is really IJ, I comma J, EIH minus EJH square. Do you agree this thing, Manoj? It is sum of the diagonal elements. That's Manoj.
Yeah, just give me a second. Is equal to trace of add h whole square.
Oh God. Sorry.
Add h is this square h. This is
Okay, let me explain this thing. So you write this thing. Suppose U11, U12, U1n. Okay. So E21, E22, E2n. These are my bases, right? E, N. These are my bases. So with respect to this U11, if I will write this matrix okay, what is the matrix representation of RH square? This is really E11, RH square E11, this will be 0. Okay. So see, the thing isn't it clear? Okay, think for a moment. Okay, I am giving 1 minute.
no. So B h comma h is
Trace of RH square. And RH square is a diagonal matrix with these are diagonal elements.
no, that's fine. The second line to third line is fine, but
Fine.
BHH is
Trace of RH square and IJ is equal to EIH minus EJ square. Is there anybody who is not able to follow this thing? Manali, is it clear?
Yes, it is clear.
Santanu?
No, why BHH is equal to trace of ADH square?
that is definition, I think, right?
That is the definition.
Okay, okay, then it is clear.
So you should ask Santanu. You should not. Okay. So this is really IJ EIH minus EJH whole square. This is really I comma J EIH square. I am just opening this thing plus EJH square minus 2 into EIH into EJH. So what I will do, I comma J, this is really EIH square. I will separate this thing, IJ EJH square minus 2 times IJ EIH into EJH. So now what I will do, I will first fix this J and I will sum this thing EIH square. Now I will fix I, then I will sum this thing EJH square. Okay. Minus 2, this factor, this term actually we have calculated. So if I have, you have calculated that thing is trace of H square, this B. So this I can write this thing minus 2 into this is trace of H whole square, right? This is from B, this is clear. Okay? So this is really now J, and this term is really trace of H square. Let me write this thing. Trace of H square and plus I trace of H square minus 2 into trace h whole square. I am summing this trace of h square n times because j is from 1 to n. Similarly, I am summing this is from I equal to 1 to n. So n times trace of h square and plus n times trace of h square, 2n trace of h square minus 2 into trace of h whole square. Okay. So hence for h belongs to delta, we get this thing b h comma h is equal to 2n into trace of h square minus 2 times trace of h whole square. Right. Okay. Now let x belongs to d. So what is d? D is really x belongs to MNC. So that x has distinct eigenvalues. Actually, these are called regular elements. Okay. So this I am what I. I think somebody has to move. Hello. Yeah. So x belongs to d. Okay. So let x belongs to. So this is.
So you're saying these are called regular elements. This dense,
yeah.
dense set.
Yeah. So first proposition I have proved that regular elements are dense in MNC. Okay. So this now okay. X is diagonalizable. So there exists G belong. So there exists G belongs to GL and C. So that G X G inverse is equal to H. This belongs to delta. This is a diagonal. Now B X comma X. The Killing form is RG invariant, right? So this is really B of RG X comma RG X. And in the Matley group case, this B RGX is equal to really GX G inverse. And this is equal to GX G inverse. So since RGX is equal to really GX inverse. So that will B of H comma H. This is really 2n into trace of H square minus 2 times trace of H whole square. I am using the since H belongs to delta. So as H belongs to delta. So we have proved that expression for H belongs to delta. Okay, this expression, let us call this as C. I am using that. Okay, so now what is H square? H is equal to GX inverse. So H square is equal to really trace of G X square G inverse. Minus 2 into trace A in place of H, I am replacing this as GX G inverse square. So now 2n into trace of X square minus 2 into trace of X whole square. So hence we get what? Hence this B of X is equal to 2n trace of X square minus 2 of trace of X whole square. This is really X belongs to D. Now as this thing Y going to this BYY and Y going to trace of I square and Y going to trace of Y is continuous on MNC. And this are continuous functions on MNC. MNC, and D is dense in MNC. So by continuity, this will hold true for any Y belongs to MNC. Then thus it follows that see this any linear map on the finite dimensional space is continuous. Any bilinear map also on a finite dimensional vector space is always continuous. Thus it follows that B of yy is equal to 2n trace of y square minus 2 into trace of y whole square. This is really y belongs to MNC. Hence the claim. So we have proved the claim. So hence we have proved thus and thus for xy belongs to MNC, we get this thing B of xy is equal to 2n into trace of xy minus 2 into trace of x into trace for all xy belongs to. Now I have proved a result. If you remember, if G is a complex Lie algebra and G naught is its real part, then this BG and BG naught are same. Okay. BG restricted to G naught cross G naught is same as BG naught. I have really showed that. Okay, so let corollary.
So you want to say that on M in R also it has the same form?
Yeah. Let G is equal to either GLNR or GLNC. Okay, GLNR or UN as okay. So let us say as GLNR complexification is equal to GLNC equal to really UN complexification. Hence it follows that so BG x comma y equal to 2n trace of xy minus 2 into trace of x into trace of y for all xy belongs to. Okay, so this is I think. Okay, so now we will calculate the killing form of SLNC. So you know that here actually, so I have to do the proof for MNC because the diagonal elements are dense in MNC only. Once diagonalizable matrices are dense in MNC, but for MNR, if I will straight away do this, then there will I will face some problem. Okay, so now, so let us start with a proposition. So let okay, so let so eta okay, let G be a Lie algebra over K with K is equal to really R or C. So let eta subset of G be an ideal of G. Then if you look at this killing form restricted to eta cross eta, this is same thing as B eta. Precisely. If y comma z, this is belongs to eta, then beta g y comma z is really beta eta y comma. This is proof is easy. Probably some of you have seen this thing. Let s is equal to really x1, x2, xk, xk plus 1, xn be a basis of G, so that this S tilde is x1, x2, xk. This is a basis of, okay, so basis of eta. So what I will do, I will choose the first kth element, this x1, x2, xk. This belongs to eta, I will take that. This belongs to real letter side S tilde, and this subset of eta. So then I will extend that basis to get a basis of G. Okay. So that is the way. So let so what is S? So S tilde is S is equal to really. So this is the x1, x2, xk, and xk plus 1, and really xn. Now let y comma z. Y belongs to eta. So I look at this thing Rg of y. I will look at this Rg matrix representation of Rgy with respect to this S. Okay, so I want to write that. Now, what I just look at this yx1. Since this x1 belongs to eta, so this and eta is an ideal. This y of x1 belongs to eta. So what I will get up to this kth element, kth row, there will be something here, and after that I will get 0 here. And similarly for second row also, this up to this kth row, I will get something here, and after that I will get 0. And this will go on for k cross k. This will go up to this kth column. Okay. So if you will think little bit, and this is really what I will get. So I will precisely get this thing. This is really R eta y. This is really S tilde. Matrix representation of R eta y with respect to x tilde and 0. Okay. So now okay. So now I should look at this thing y of xk plus 1. Now since y belongs to eta here, so this belongs to eta. This y leave bracket of y into xk plus 1. This will belong to eta. Similarly, up to kth row, I will get non-zero entry here, and there after that will be 0. So this will be something like ay, and this is 0. So okay, Ushchab, is it clear?
Yes, it is clear.
Okay, so similarly, if z belongs to eta, so you will get this thing Rg zs is equal to really R eta z s tilde, something like az and 0 0. This az is really, this is actually what, this is k cross n minus k matrix, and similarly this is a k cross k matrix, and similarly you can get what are the dimensions k cross m minus k. I am really writing this m minus k, m x. Okay, so now let us do that. So okay. Now let us see at g y r g z matrix representation of this with respect to this s. So this you will get that rgy s and rgz s. So this you will get this something like r eta y s tilde. This is really a y 0 0. This is really odd eta y s tilde. This is the result 0. This will be az. So that will give you odd eta y s tilde into odd eta z s tilde, and I don't care what is there, and this is 0 0. So I will write another line here. Okay, so let us go to the next page. So that will give you this will give you odd eta y, odd eta z is tilde. This is, I don't care it what is here because I want to calculate the trace. So taking trace in both sides, taking trace in both sides, we get this thing. So odd eta y, oh sorry, okay, I will get trace of odd gy, odd gz. This is equal to degree trace of odd eta y, odd eta z s tilde. So this is really b g y comma z. Eta b eta y comma z. So this is really okay. So hence this is, so we have proved that. So hence the proof. So we get this bg y comma z is called beta y comma z, and we need to prove this thing. So a remark. So if eta is subset of G is only a subalgebra, but not an ideal in V, the above proposition may not be true. Proposition may not be true. For example, you can so you take G is equal to any GLNC. So let us okay. So let us do the simplest case. Actually, this example will true for more general, but let G is equal to really GL2C. Okay, so let us say X is equal to really 1 0 0 minus 1. So what is BG X X? This is equal to 2n trace of x square, and n is here 2. This is really 4 trace of x square into 2 into trace x whole square. So 4 and the trace of x square is equal to what? Trace of this is 1 0 0 1 because, and trace of x is equal to 0. This is really 4 into 2. This is 8. Okay. Now let A is equal to really span of this thing x. So this is really what? So lambda 0 0 minus lambda. So lambda belongs to C. And as so clearly this A is a subalgebra of GL2C. Now as A is abelian, the scaling from BA is equal to really 0. But here this implies BA XX is equal to 0. and this is not equal to really b gx. So there is nothing special about 2 case. So you can also construct counter example for n greater than equal to 2, and this is not now. So okay, so let us set this question. So let a belongs to a comma b belongs to GLNC. Then if you look at this Lie bracket of AB, this is really AB minus BA, and this belongs to SLNC. This is because since trace of AB is equal to really trace of ABA. Trace of. Okay. So hence what you get, hence GLNC, if you take this thing, Lie bracket of GLNC and GLNC, this lies inside SLNC. Okay, so I want to take this thing. So this implies SLNC and GLNC. This is really subset of GLNC, and this is really subset of SLNC. So what I'm getting here, this implies SLNC is an ideal of GLNC. Okay, so let eta is equal to really SLNC, and G is equal to GLNC. So as eta is an ideal in GLNC, by applying the previous proposition, we get this thing. So we will get what? Beta eta xy. This is really where you take this xy belong to small SLNC. This is equal to beta g x comma y, and beta g x for y 2n trace of xy minus 2 into trace of x into trace of y. But since x belongs to SLNC, this is equal to 0. So this thing is really vanishes. This is equal to 2n. So hence you get this beta eta xy is equal to 2nxy. This is the killing term for SLNC. So let us write the final thing. So let G is equal to really SLNC or small SLNR or SUN. Okay, so let us write or SUN. Since okay, so this SUNC, complexification of SUNC is really SLNC is equal to really SLNR complexification. So hence we get that BG x comma y is equal to really 2n into trace of xy. This is really for xy belongs to. So this is the expression of the killing form of this thing. So now, okay, so if we put this y is equal to x star, so we have already seen that these are really semi-simple. How did you prove that these are semi-simple? This SUN is a compactly algebra, and it has really centered place. How do you conclude that it is centerless? Because the Lie group SUN actually is just finite. For that reason, this is center line. Therefore, SUN is really a semi-simple Lie algebra. Then since SUN is semi-simple Lie algebra, its complexification SLNC is also semi-simple Lie algebra. And since SLNR is a real form of SLNC, therefore all three Lie algebras are semi-simple. We have concluded that. But you can conclude this Lie algebra is semi-simple by directly directly calculating the killing form, and we have calculated that. So if and for to calculate that, we do not need any. This is an independent thing. Okay, you do not need the previous result. If y is equal to x star, this bg x star is equal to really 2n base of x star. This is equal to 0 if and only if this is really x is equal to 0. Hence, this radical of bg is equal to really 0. Therefore, therefore G is semi-simple. So this gives another proof. Okay. Similarly, if you see this thing is I have proved that this some Riemannian pair SUN and but what is that SUN and I think ON SON SON. This is a compact Riemannian symmetric pair of compact type, right? So you can also prove that thing using this expression of the killing form directly, because you have to calculate this P and you have to show that this BC is restricted to P is really negative definite. You can show that. Okay. So now I actually calculated the two killing forms. Actually for SONC and SPNC, I will leave this computation and this because actually you can read those things in Helgason book, but the thing is you can verify the steps, but you will not understand the proof because properly. If you to understand the proof properly, you need to know a little bit about something called Cartan subalgebra. If you have idea about those things, then you will understand the thing proof. But if you do not know those things, but still then you can see the proof and you can verify that proof. So verifying a proof and understanding a proof is very two different things. So as I have said that today will be the last lecture. So what I will do now, I will just state 2-3 simple results. Then after I will stop. Okay. So by saying something. Okay. So this is a very important theorem. So let M be a simply connected Riemannian symmetric space. Then M is written as M can be written as M0 plus M plus cross M minus. Okay. Where and this is this is actually M can Riemannian product. Okay. So where this M0 is a Euclidean space. This M plus is a RSS of compact type, and M minus is a RSS of non-compact. Okay. So proof you can see Helgason. Now this is the theorem, and this theorem will be useful in classifying Riemannian symmetric space. And now I want to state
No,
another example you want to see. Actually,
yes.
you can look at this thing. Actually, Okay. So I
See, I
can
understand
tell you,
one part has curvature 0, one part has positive curvature, one part has negative curvature. Is it like that?
yeah, curvature 0, curvature thing. M0 has curvature 0, M plus has
Yes.
curvature positive, and M minus 1 is sectional curvature negative. I told you that if something is a compact type, then it has curvature really greater than equal to 0. That would not be really strictly positive. That may not be equal to 0. Identical equal to 0 may not be identical to 0 if RSS is a compact type, and it will be really greater than equal to 0. Okay, so example I can tell you that, but I don't. So you look at this thing, GL plus NR, and this is really ON. So this is actually simply connected Riemannian symmetric space. This can be written as R cross SLNR plus S1. So this thing is actually, you can prove that this is neither Euclidean type or compact type or non-compact type, but it is simply connected Riemannian symmetric space, because you can identify with this sort of all positive definite matrices Pn, and we have shown in the class somewhere in the first class, this is actually simply connected, and for that reason actually you can actually have a decomposition like this. So R is a of equivalent type, and this is really non-compact type. And there are other examples also. For instance, you can, so one lame, this is an example. One lame example will be something like this. You look at this SLN, any, you have some symmetric space M0 of, okay, you look at this thing, Rn, okay, something like SNLR mod SON, and this is really SUN mod SUN. So this is really of Euclidean type. This is really okay. So let us remove this thing. You write this as GKC. But for the time moment, I was not sure about it. This is really non-compact type, and this is compact type. Actually, I wanted to prove this theorem, but I don't have much time now, so I am just avoiding it. So this is the thing. So now I told you. So okay. So suppose G comma H is a Riemannian symmetric pair. Then if suppose, so let us write on another page. So So G comma H is a Riemannian symmetric pair. So G acts on, suppose G acts on G mod H effectively. So then I have told you that G, you can think that G is a subset of really I G by H. So I have discussed this thing. Okay, so this is really, let us write AM dot, where AM is equal to really G mod H. So you can now our question was, when G is equal to really IM naught. This was the question. And I have, okay, so I have given some example where we have seen some example, where this G is properly contained inside IM naught. Where G is not equal to IM naught. And whatever example we have seen, these are really of Euclidean type. If you will check that Riemannian symmetric pair is of Euclidean type. Okay, so now if G comma H is a Riemannian symmetric pair of compact or non-compact type, then G will be really IM naught. So let us write that proposition. Okay. So that G comma H be a Riemannian symmetric pair, so that G acts on G mod H effectively. Suppose G is semi-simple. Then G is equal to really I G by H naught. Proof you can see. Okay, so actually, okay, so this is the corollary. I really, you know that if so let
Just can you say in this case that this will be compact or non-compact type?
I am saying that I am going to let G be a H. In this case, you cannot say this is compact or non-compact type because you can always make a product of compact and non-compact type.
Oh.
Okay, so M1 is of compact type, M2. The
One-way
group
implication, right? If it is compact or non-compact type, then it is semi-simple. Then the group is semi-simple, right? So other way around is not true.
Yes. So G comma H P an effective Riemannian symmetric pair of compact type, compact or non-compact type. Then G is equal to I of G by H naught. Oh, compact type and okay, I have to assume more. And G acts on G mod H effectively. Then G is equal to I. This is the thing. So actually, I have plans. I have planned to cover so many things, but I could not do many things. And with this, actually, I would like to stop. And also, the thing is, actually, as I am thinking to give another set of lecture, probably after 6-7 months, and but I am not so sure that I will be able to give or not, because always time is the factor. So, but if I will give those lectures, that will be very nice, because I can cover some interesting things, and the things which are required for analysis are really in the second thing actually. So I hope all of you like my lecture, and also I am thankful to Thangavali sir and Pritam, Pritam, for organizing this thing lecture series, and I am also thankful to Rajesh Bhaiya for recording my lecture, and I also would like to thank also Sayanda, who always stimulated me to give some lectures on symmetric space or representation theory of SL2 or like that. So I hope you have liked my lecture and you have learned something, and you don't come out, don't go away from this WhatsApp group. If I will means I will feel like lecturing something, then I can message you. And with this, I would like to stop. And if you have any question, you can ask me.
Thank you very much, Muna, for these lectures.
I think all of
let's
us,
thank
all
the
of us should
speaker.
unmute and thank him.
Yes,
Unmute and this was a non-trivial job, and then Muna continued for so long. And it's nice series of lectures.
You liked it, sir?
Yeah. I mean, but I missed several lectures, but then it is very, very nice. I mean, you are not just asking questions during lectures, but you are also a very good lecturer. Actually, unless you are a good lecturer, you cannot trouble asking questions in another's lectures.
Rajesh Bhaiya, do you want to
So
say
Muna, why don't you give a research talk someday?
something? Research talk.
Yes.
I will try, but
About your work.
yeah, actually the thing is, Swagata sir is saying something or something. What? SKR. Okay.
Yeah.
Okay, so actually, I don't know.
Someone is
if
raising hand, I think.
Rajesh.
Rajesh.
No, 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 no.
Yes, Sagat sir is there, but
Nothing.
Okay. Okay, I will see. We will see that actually. Okay. Then Pritam, you should stop recording. Okay. Oh, Sagatu sir.
yeah. So please upload the lecture notes.
Yes. Okay.